Hello, and welcome to this session on machine learning. What we'll be doing is taking a look at what machine learning is, the kinds of problems that machine learning can solve, and leave you with a sense as to what skills you will learn if you follow up on learning machine learning. So, what we'll be seeing is what machine learning is, some important types of machine learning, in particular, things like supervised and unsupervised machine learning. Don't worry about it. We'll explain what those terms mean, give examples, and we'll also talk a little bit about some interesting things that are going on around machine learning, interesting challenges, interesting ways in which machine learning can be deployed on the cloud, and what companies are doing with it. So, welcome to machine learning, and let's begin by getting a sense of what machine learning is. What is a machine? A machine, by and large, is something that moves. But what is moving here? Is there a mechanical device that machine refers to? In general, no. The kind of machine that is referred to in machine learning is a computer. Now, the computer can move, for example, if it looks like a robot. And one part of machine learning is certainly involving building robots and having them do things. The field of AI, or artificial intelligence, is built around that kind of thinking. And that is certainly an application of machine learning. But in general, machine learning is about teaching a computer to do certain things and do it in a way such that at the end, it does the task by itself without being explicitly programmed to do something. This is the learning part. What do you mean when you say you are learning something? It means that there has been a process by which some teaching has happened, and based on that teaching, you can do things by yourself. You have learned how to do things. It's the same idea. We're teaching a computer. We are programming it to learn certain tasks so that when it does these tasks, it does not need to be explicitly told again how to do the task. Now, all this learning happens via a software, which is how we usually implement a program. So therefore, the problem of machine learning becomes the following problem, that how do we write a program that can learn and do things on its own? For example, it might be able to identify things. Let's say, identify fruit based on color, size, shape, or anything else that is input with respect to the fruit. So the idea in this example would be to say, can I write a program which effectively tells the instruction that should you see this new kind of fruit, maybe the picture of a fruit, the image of a fruit, and then say, what is this fruit? So, for example, I can take a fruit. I'm reaching out now and I say that, let's say, what kind of fruit is this? And the computer, based on the image of this fruit, may be able to say, oh, this is a banana, or this is a set of bananas. And so therefore, what a computer needs to do is reach that conclusion. Now, how do you think this will happen? What needs to be in that program so that this kind of learning happens? Well, the easiest way to do that is to essentially tell the computer what a banana looks like by giving it images of lots and lots of bananas. You are correct. You need to tell the computer by giving it data about bananas. So therefore, machine learning, a large part of machine learning is essentially about data, because it's through this data that the computer learns, that the machine learns, and the program is about being able to process this data and extract information out of it. So a lot of the steps in machine learning are about data and the analysis of data. In fact, the process begins with gathering data. Gathering data on fruit in our example, gathering data of bank customers, for example, gathering data on people who have communicated on social media, for example, gathering data from satellites that are taking pictures of, say, oceans where storms may be starting or fields where crops may be growing, all kinds of data from which we want to learn something and program a computer to learn the same thing. After the data has been gathered, the data has to be prepared, which means it has to be made suitable for learning. For example, we might need to tell a computer, this is a banana. That is preparing the data. It's not just the image of the banana, it is also telling the computer or attaching the label banana to the picture of the banana. That is preparing the data. Once the data has been prepared, you choose a model. What do I mean by the word model here? We will see or maybe allude to examples of a model soon. But what a model means is it is a way to translate the data to a form of learning. Essentially, it is an equation that says that this part of the picture of a banana, let's say the yellow color, is something that translates. The yellow color is, let's say, an input into the model, and the output of that may be the label banana. That is a model. And so what a model does is that it translates certain features of the data to certain outputs that we are interested in. And so therefore, this is usually a mathematical expression that is coded into the computer. The next part of this is, once we have said this is what my computer program has to be able to do, is we need to train the model. Train the model means to say, okay, what inputs of the banana actually identify it as a banana? Is it the color? Is it the shape? What part of it is that? Am I interested in identifying this banana by yellow, or is it this particular shape that this banana has? What part of banana is this model going to be trained on to realize that this is important? That's training. Once we have trained the model, the important thing is to know, was the training any good? Could it, given a new fruit, identify it as a banana? That is called evaluating the model. Or did it say for a banana, no, this is not a banana, this is an orange? In which case, it'll get a low score, a low evaluation. It's like the machine learning algorithm is going through an examination. If it passes, that means the data is good, the model is good, and the training is good. And so the evaluation is passed. But even after passing the evaluation, you can say that, can I make it even better? For example, let's say that you've made a suit, you've stitched a shirt, or a tailor has stitched a shirt. Can I make a little adjustment here and there in the collar or somewhere else? Maybe I need to press it a little bit. Can I tune the output in order to make it more suitable for a particular application? This is called tuning the model, sort of like tuning a radio. The word tuning comes from, it's an old-fashioned term. It means a tuner of a radio saying, is the reception very good? Or is it, and then you tune it and it becomes very good. And after the tuning is done, then you deploy the model. Deployed means you use it to predict things. You use it to say, oh, this is a fruit, this is a banana. Or if you are making, let's say, a car, this is a pedestrian, this is a light. Or let's say you're approving a loan, this is someone I should give the loan to, this is someone I should not give the loan to. Or you're treating a cancer patient and you look at a tumor, an image or data from a tumor, and you say this is a benign tumor. Okay, this is a malignant tumor, very bad, we have to do something right now. So you put it to use in prediction. So let's review a little bit. Get the data, make the data suitable for analysis, connect the data to the kind of outcome I want, the model, train the model to do the right thing, that is, perform its job very well, evaluate whether in fact the model is doing a good job or not, then tune it for the application that I want it to be used in, and then use it to predict. And then keep doing this over and over again. As new data comes in, learn more. As data gets put into a better model, learn better. So keep in some way doing this over and over again. Machine learning is a continuous process. Just like you and I, when we learn continuously. Our brains are essentially active, taking inputs in and learning. Maybe even when we are sleeping, our brain is reorganizing our data. And so machine learning is like our learning, it's a continuous process. Now, this way of learning is something that is a little bit of an art. It's a little bit of learning how to do things. And like every art, like everything like this, you need to practice it. And the more you practice it, the better you get. And the more people realize that you really know how to do this. And so, how can you do this? How can you learn this art? How do professionals figure out that they're good or bad? One way to do this is, for example, to participate in hackathons. Hackathons are devices or processes or competitions that effectively take you through this process and say, oh, are you good or are you not good? They are competitions. It's an event. And it is asking you to do something in a fixed period of time. And what is it that they're asking you to do? They're saying, given this data, can you give me a good model that does a good prediction in my case? It'll tell you what the prediction required is. And it will then say, given this task and given this kind of data that I'm making available, can you predict well? So if you see a hackathon, if you see it on the media, if someone tells you there's a hackathon around, or the course that you're in invites you to participate in a hackathon, please do reach out if you can. It's a wonderful way to learn how to do machine learning. And certain parts of it, like for example, training a model or evaluating it, becomes second nature if you do it many, many times. And sometimes you can even get rewarded for it. Maybe you can get paid for it or companies hire through it. A hackathon is in some way a test of the machine learning process, both for yourself, for an algorithm that also goes through many hackathons. Algorithms that are successful in many hackathons become standard algorithms. So what is a good algorithm? A good algorithm is very often an algorithm that has been used to win many hackathons by individuals or by teams. And so this is the way machine learning has been developed over the years, particularly recent years, by people trying different algorithms out and seeing if they work for different kinds of data and for different kinds of predictions. The other way you can do this to some extent is by participating in competitions directly, not necessarily in a short time-bound way, but through organizations such as, say, Kaggle. So if you go to kaggle.com, you'll see lots of data sets and lots of challenges that are out there. And these are open challenges, often with lots of time available to you. And you can participate and see how well you are doing in these tasks that are asked of you. Prediction tasks, classification tasks, maybe grouping tasks, different tasks are assigned, and winners are tracked. So again, like in individual hackathons, if you are, say, a Kaggle master or a grandmaster, you are recognized as someone who has gone through many of these tasks. And many of the algorithms that are recognized today have been used in Kaggle and other competitions, such as those released by companies like Google, Yahoo, Facebook, etc., which make it possible to evaluate algorithms as well as people. So this was a short overview of what it means to be able to do machine learning and learn about machine learning through competitions. Now, let's step back from that for a while and return to what machine learning is and what it is trying to do. And machine learning has many aspects to it. I described one aspect to it, being able to identify fruit. But there are various aspects to it. Let's take a brief look at some of them. The example that I gave relates to something called supervised machine learning. Supervised machine learning. Supervised machine learning is essentially the task that says that is there a task that I'm giving the machine learning algorithm to do, and I'm giving it labeled data to supervise the task. Let's go through some examples of what this is, and it'll become a little clearer what supervised learning is. So supervised learning at its base talks about being able to identify a relationship. Remember the model that I was talking about, an input like the features of a banana, an output like, for example, whether it is a banana or not. And so this relationship is a relationship that I need to be able to find out. Now, how do I find that relationship out? I do that using a certain trick, and this trick kind of explains what supervised learning is. So I take my observations and I label them. Label them means, again, telling a banana that it is a banana, telling an orange that it is an orange, telling an apple that it is an apple, whatever you want to be able to predict. That is called labeling. Now, this labeled observation is then used to train the model. Training the model, as I'd explained, is to be able to say, has the model been able to learn the label? This label is serving like a supervisor to the data, saying that I'm telling you that this is a banana. Are you learning that this is a banana? Are you getting trained? This training set, therefore, is something that tells the algorithm that I'm figuring out what this relationship is between the input and the output. The input you can think of as the data, the image of the banana. Let's say this may be various images of bananas, could be, for example, in various forms, directions, etc., could be my data, and the label would be this is a banana. Now, whether you have learned this or not is evaluated on another part of the data set called the test data set. And the test data set is something on which this learning is tested, it's evaluated, which means that on this test data set, there will be images of fruit, and you will not know which fruit it is. And then the algorithm predicts. And now somebody will tell you, oh, the real label is so and so. And you say, how often did I get it right? And how often did I not get it right? It is testing the model to see whether the label identification is correct or not. And so this tests what? It tests the ability to predict, because it says now that if I give it the observation, it can predict the label. And how good that prediction is evaluated on the test set. So the model is now predicting. The model learned on the training set is predicting using various kinds of methods. And whether those methods work or not is evaluated using certain statistical techniques, which could be as simple as saying, what percentage of the time was I correct? Just get that statistic to be good. Be correct 90% of the time on my test set. Be correct 95% of the time. If you are correct, say only 70% of the time, then 3 out of 10 times you are not making the right decision. That statistic is now telling you that your algorithm is not very good. This is the broad premise of what supervised learning does. Depending on what the kind of labeling is, there are different kinds of supervised learning that we often use. One is called regression, where the label, so to speak, is not a label at all. It is actually a number. A number. In other words, what I'm trying to learn is not whether something is a banana or not, but I'm trying to figure out what the number should be. For example, I might try to find out what should be the price of a house if I give you information about the house. I might say that tell me some data about the house, the number of rooms the house has, what kind of house it is, what location is it in. Give me that kind of information. Using that information, which is my X, I'll now be able to say, this is my Y. And what is the Y? The price of the house. Think of what this can do. What it can do, for example, is if you're a buyer of a house, you can look at a house and you'll be able to guess how much I might have to pay for it. Similarly, if you're selling the house, based on the features of the house, you might be able to say, how much can I ask for this house? So therefore, these kinds of models in predictive mode develop this relationship between variables. These variables often have names. For example, this price variable is sometimes called the dependent variable or the outcome variable. It is an outcome and it depends. What does it depend on? It depends on the independent variables, which could be, say, the number of rooms of the house, or it could be other features of the house. So therefore, this particular task of machine learning is to use independent variables to build a model that can predict the price or the value of the dependent variable. And you can think of many particular applications of being able to predict a number like this. Some of them could be very valuable. For example, being able to predict a stock price can make you or an organization extremely rich. Or being able to predict when the monsoon will come and what kind of rainfall this monsoon might bring would be very useful predictions to have for a variety of industries, particularly, shall we say, farming or agriculture. So, this kind of supervised learning refers to predicting a number. The other kind of supervised learning refers to another kind of label that we've already seen, and that is a classification problem, which is identifying a label. In our case, it was a fruit, but it could be something else as well. For example, you might be looking at, can I identify the label associated with a handwritten number? So someone is writing numbers. Let's say they're writing zip codes or pin codes in a letter. We don't write letters anymore, but still, can I read numbers? Can a computer identify a 1, a 0, an 8, a 7, etc. from handwriting? This is like showing a picture of a fruit and being able to say what fruit it is. It's by looking at various aspects and say, for example, at the bottom here, I'm circling a 7. There is another 7 near the top that looks a little different, but the human eye can say that's still a 7. But it may be different from, let's say, a 1, which is the top left corner. Now, this 1 and the 7 that I pointed to second look similar, that they have the same diagonal line. But what is the feature that might allow a computer to correctly classify, correctly label each of these symbols into saying this is a 1 and this is a 7? What are the features? I talked about color, shape, etc. What are the pictures? What are the aspects of the image? The pixels, do circles represent a 0? Is an 8 represented by 2 circles? So if I see 2 circles of this kind, am I then going to classify it as an 8? Rules like those. Should 2 necessarily have a little wiggle or a circle at the bottom? But some 2s do not. And so therefore, these rules are learned by giving it a lot of data, many handwriting samples from many people with different styles, but with somebody giving the computer the right answer so that the computer can find the right characteristics of the image, of the object that it is seeing, and link it to the label it is supposed to identify, which in this case is a number. So in summary, what is supervised learning? Supervised learning is the learning of a rule that either predicts a number like regression or a rule that predicts a label like classification. How is this rule learned? By essentially giving data and giving a training set in which many rules are tested out, and then the test is done on a separate data set called the test set. And this test set performance is evaluated to see whether I predicted the number well or I predicted the label well. Has supervision worked? Has machine learning worked? In fact, remember the hackathons and Kaggle that I talked about? Those essentially ask you to work on a training set. And then, in some sense that I won't make too clear now, they have a test set at their disposal and they give you the test set and they say, now tell me how well your algorithm does on the test set or what your answer is on the test set, and I will tell you how well you have done. And based on who is doing well on the test set, I'll create the leaderboard. And so these are often used as ways to continuously evaluate algorithms. Now, in supervised learning, this is an easy thing to do because the purpose is clear. But in certain cases, the purpose of the algorithm may become a little less clear. And those kinds of algorithms, that kind of machine learning is often called unsupervised machine learning. There isn't a supervising variable or a supervising task that is obvious or present in the data. Unsupervised machine learning has many more styles because, as I said, it doesn't have a label to go after. So what might be some important problems or examples associated with this more hazier kind of machine learning? Here are a couple of examples. One is the example of clustering. Clustering means forming clusters. What are clusters? Groups of things. So essentially, the unsupervised learning problem is the problem of finding groups of things that can be thought of as together. For example, grouping users based on search history. This class of users is interested in this topic. Let's say they are interested in astronomy. Another class of users may be interested, let's say, in football. So based on their search history, based on their online characteristics, you can group them into different kinds of users. Maybe another kind of user is mostly paying his or her bills online. So to do similarity of this sort, you need to be able to find features and you need to be able to find distances between features. Small distances, same group. Large distances, different groups. That's what clustering tries to do. You can imagine that this is a very important thing in certain commercial applications, like in marketing, where marketers tend to think of segments. This segment buys my product for this reason and lives in this area. This segment buys my product for a different reason. So therefore, segmentation and therefore targeting and positioning is a very important task in marketing that is driven by clustering, which is a form of unsupervised learning. Marketing and many other applications also think of another kind of unsupervised learning called association. Association means if X, then Y. If A, then B. Or A and B together imply C. People who bought A and B also bought C. People who bought bread also bought butter. Things of that sort. So therefore, association and the rules built around association find connections between variables. And very often these can be very complicated or long-reaching connections. Say, for example, websites going from one website to another website to another website. Websites often have characteristics called hubs and authorities. Hubs are websites where people come into. Authorities are websites that people go out of, so to speak. So therefore, hubs and authorities establish associations. And so association rules are one of the older forms of unsupervised machine learning. And we'll see something very similar to this soon coming up. That's going to be important to understand how machine learning gets used in these kinds of unsupervised settings. So unsupervised machine learning is effectively about looking at data without a specific identification of rule in mind. I'm not going to tell it what kind of clusters to find. Let the data tell me what clusters are out there. I'm not going to ask the data to sign what is the rule that's on the right-hand side? What is it that people are buying? I'm simply asking data to sell, if people buy this, then what do they buy? And what combinations are important and what they are not? There are particular kinds of unsupervised machine learning that are important. But before we move on to that, let's figure out a difference between supervised and unsupervised learning by kind of putting them together. Here's an interesting example. Let's suppose that the label associated with this data is a label of noughts and crosses, zeros and x's. Now the label naught is associated with these 4 points that you see on the left picture, and crosses are here. Now this is a supervised learning situation where the rule would be to say that what values of x and x1 and x2 lead to noughts and what value lead to crosses. For example, you could come up with a simple rule that says high values of x and x1 and high values of x2 should be predicted as crosses. Low values of x1 and low values of x2 should be predicted as noughts. That is supervised. The unsupervised version of the same problem would be that there are no noughts and crosses. They're all noughts, say. But tell me how many kinds of noughts there are. And the algorithm should be able to say, you know what, there are two kinds of noughts. There is one kind that corresponds to low x1 and low x2, and another kind that corresponds to high x1 and high x2. And within these kinds, within these clusters denoted by the red circles, the points are close by. But between them, they're further away. Similarity within clusters, dissimilarity across clusters. Now, this leads to an interesting idea that there could be things that are, shall we say, semi-supervised, where in some parts of the data you know the label and in some parts of the data you do not know the label. Or it could be in the following way. First, use unsupervised learning to find the label, and then use supervised learning to learn the label. And those lead to very interesting applications, particularly applications where you don't particularly know to begin with what might be important, but as you figure it out, you then try to do the important things well. And many of the modern applications in AI have that look and feel. So modern machine learning is kind of folding supervised and unsupervised learning into each other a little bit. And the distinction that was there is slowly disappearing because both of these tasks often have to be done realistically. Think about how you learn. Sometimes you learn without knowing what the patterns are. You learn the pattern. And in some cases, you know that there is a pattern. You just want to know what the pattern is. That is the distinction between these two kinds of learning. Now, unsupervised learning itself can have connotations that lead to interesting predictions. Remember that prediction is a supervised task, but unsupervised learning is a pattern discovery kind of task. So let's go back and talk about one of these competitions a little bit. And I go back now a few years to 2006 to 2009, and Netflix, then not the media behemoth that it is now, but Netflix had movies that it was distributing online, and it wanted to know, can I make the right recommendation about movies? Can I figure out whether X will like this particular kind of movie or not? In other words, can I make recommendations? And to do those recommendations, it said I need to have a certain kind of algorithm that it was calling a collaborative filtering algorithm. And this is mostly an unsupervised learning algorithm, but as I said, there's a prediction feature to it that I think you'll find interesting. So here's the problem. Once again, the problem is, given people who watch movies and people who give inputs on movies, so you know people watching movies, what movies they watch, you also have certain information about what they think of the movies, let's say ratings. Now, using this, you want to be able to make a prediction or a recommendation to another user saying what movies might you be interested in. That's the problem. Think about how you might solve this. This is a problem that involves users, people who watch the movies, and items, the movies themselves. And how do I put users and items together in order to make recommendations? So recommender systems are things that effectively do this. And they do this using a variety of methods, not just collaborative filtering, which is what Netflix was interested in. But recommender systems are there everywhere now. You see it all the time. For example, let's say that you are doing a Google search, and based on your search, Google recommends something. You go to YouTube, and your YouTube system is making recommendations of what videos you might watch. In fact, Netflix itself, if you see on television now, it will give recommendations and suggestions as to what else you might be interested in. And so, what do these recommender systems do? And what kind of machine learning is this? So there are various kinds of machine learning algorithms that go into recommendation systems. Some of them are based on pure classification model based. They're essentially modifications of supervised learning to say, can I classify this? These are the different kinds of bundles that I have. Let's say I have science fiction movies, I have romance movies, I have adventure movies, I have historical movies, I have children's movies. These are classifications. Which one will I recommend to you? And the classification is done. I'm simply deciding which of them. So these are classification-based systems. They could simply be based on popularity. This is more statistical in nature. What are most people watching? If most people are watching this, it's quite likely you will also be interested in watching this. Commonly viewed movies, for example. This is almost as simple as counting. They could be about association rules, which is what I said. A and B, then C. Historically, people have watched this movie and the second movie, and I'm going to recommend the third movie. They watched, let's say, The Godfather Part 1 and then Godfather Part 2. I will recommend Godfather Part 3. Or the Star Wars movies one after another, or the Marvel Cinematic Universe movies one after the other, based on A and B recommend C. Or they could be based on, shall we say, nearest neighbors. What are the closest kinds of movies to the kind of movie that you have? Now I need to determine what close means. What is a similarity in movies? And there are AI-based solutions based on something called deep learning, which put all of these things together and base really sophisticated online things that the best companies in the world are now doing, using AI for recommendation systems. But let's go back to collaborative filtering and come up with simple ways to think about what similarity might mean. Because if I have similarity, I can then understand what is similar and therefore what I can recommend to you. For example, think of two users, user A and user B. User A has a set of movies and a set of ratings, which is on the left. User B has another set of movies and another set of ratings on the right. Now, here's what I can say. I can say that are there movies that both user A and user B have seen? So, for example, user A and user B have both seen movies 3 and movie 4. Movie 3 and movie 4 have been seen by both users. And here's the interesting thing about these two users on these two items. They have rated the movies similarly. Movie 3 has been rated 5 by both users. Movie 4 has been rated 1 by both users. Because they have rated the same item similarly, these two users are now similar. Because I would assume that they have similar tastes in movies. Therefore, if, for example, user B is also seeing movies 7 and 8, these are then movies that I might feel comfortable assigning to user A as a recommendation. Why? Because user A and user B are similar based on their ratings, therefore the preferences of one is transferable to the other. In other words, similarity has been used. Similar users have been identified based on their ratings, and then the decisions of one are being used as recommendations to the other. Interesting, isn't it? Being able to sort of combine users and items in this particular way and finding what the notion of similarity is. This notion of similarity, if you remember, came up where? It came up in unsupervised learning. So therefore, this is an unsupervised learning idea that says which users are similar. But it is solving in some way a supervised problem, which is a prediction for what this other user might like. But I'm not using a supervised technique. I do not know what the other user likes. I'm not using that information to figure out what might work. I'm using the information of similarity. To make a prediction for B, I'm finding who is similar to B, that is A, and finding out what A likes, and then saying, based on that, what B might do. And the similarity is based on the thing I'm predicting for. And so this is what machine learning is doing. It is getting ideas from different kinds of learnings. Learnings of prediction, learnings on labeling, learnings on clustering, learnings on classifications, on recommendations. All this is coming together in machine learning in order to write programs that allow you to train the computer to do these specific things. Now you can sit back and think that how can I write an algorithm to do something like this? How can it measure similarity? What piece of code will do that calculation? Is it like calculating distances between objects? Is it like a straight line? If so, how should I calculate that straight line? And then given that, how do I group people together? How do I label them? How do I identify them? All that now needs to be worked out. Is this easy to do? It isn't. But there are things that will make it very easy to do. And one of the things that is making machine learning very easy to do is cloud computing. What is the cloud? The cloud is a piece of computing, a computer, software and hardware that is existing away from where the application is. In this picture, the cloud is away from the brain. You can think of the cloud in the sky that you see. Water vapor goes up into the cloud. Something happens inside the cloud and rain falls. Similarly, the cloud, data goes into the cloud, something happens in the cloud, and a prediction falls out. You can think of it that way. So there are programs in the cloud that allow you to execute on machine learning without necessarily doing all these difficult things themselves, without being able to talk about what is the distance, what is the algorithm, what is y equal to fx. No, a piece of code on the cloud will do this for you. Where is the cloud? What is this sophisticated thing that I'm talking about? There are companies like Microsoft that have cloud applications built, and they brand it, for example, in Azure ML. Azure Machine Learning is a particular set of cloud programs that Microsoft has made available. Amazon Web Services, AWS, is another set of cloud applications. You can access these online. You can give your data to these services. You can give the label. The cloud service will do the machine learning for you and give you back the answers. If you don't like it, try another data set, another set of labels, identify another algorithm. The hard numerical things, the hard programming things are worked out for you. This is taking the hard part away from machine learning and making it possible for people like you and me to be able to do this without being expert computer engineers. And so therefore, to be a machine learning engineer today, you need to know what is on the cloud. And you need to know what are these meaning of things are. Is this a supervised problem, unsupervised? Do I want a recommendation? Do I want a collaborative filtering? Do I want clustering? Do I want prediction? If you know this and you have the data, then you have a solution to the problem available on the cloud. So welcome to this world of machine learning, which is exciting, which is sophisticated, which is all around you now in applications, and which you can participate in through hackathons and Kaggle, and which you can also do on your own by playing around with things in the cloud. And they will also tell you how to do the most sophisticated things. So what is machine learning? Machine learning is a piece of software that allows a computer to use data so that it can do certain things on its own. Supervised machine learning is that set of tasks which is about prediction, predicting labels, predicting numbers. Unsupervised learning is about doing things that combine data into groups or find relationships. These things come together in things like recommendation systems, which find similarities between users and therefore make predictions on items. And all this can be done on the cloud if you don't really want to do the programming. That is what machine learning is. Investigate more. I know you will. Play around, participate in competitions, get data, and see the fun that will come out of it, the learning that will come out of it. And then you'll build these applications on your own. See you out there.